We'll now move to our third and final presentation today. We already have talked quite a bit about geostrata. And in the, I think it was the January-February issue of Geostrata this year, there was an article about 3D modeling. And when I saw that, when I read it, I thought that is something that we need to put into the It's Money webinar series. So I got in touch with Jennie Byron, who is the Senior Project GIS Lead for Golder. Now, for those of you that are not familiar with the acronym of GIS, it stands for Geographic Information Systems. Jennie has undertaken 3D modeling for projects in Australia and across North America, and she's applying her geology background and her passion for GIS to do all these projects and come up with, as the title of this presentation says, creating art and reducing project risk with 3D modeling. She'll be supported this morning by Dr. Melissa Landon, who is a geotechnical engineer with Golder and a soft soil characterization and engineering expert. Before working at Golder, she was a professor at the University of Maine, and at that time she focused not only on soft soil investigations and behavior, but also on offshore geotechnics for renewable energy and agriculture. And with that, Jennie, the floor is yours.
Thank you, Gerald, and thank you to the Deep Foundations Institute for the opportunity to present at this It's Money webinar series. Embracing 3D modeling isn't simply about making pretty pictures to show a client or an opportunity to have fun playing with new toys. While 3D modeling is certainly revolutionizing client presentation and community engagement, there's also more to be gained from developments in the 3D modeling across the entire project lifecycle. The rich potential of 3D modeling can be harnessed to increase accuracy and efficiency, reducing time and labor, and enhance communication and decision-making, all leading to major reductions in a project's level of risk and ultimately saving money across the span of a project. Our clients have not given approval to share cost savings with third parties. However, I will generally discuss the benefits that 3D modeling provided to save money on our project budgets. Data have traditionally been viewed in 2D forms: tables, cross-sections, spreadsheets, or reports. Interpreting and presenting data in 2D requires a huge investment of time and effort, particularly when presenting data in various scales and cross-sections. Managing a complex project with generation of many 2D drawings rapidly becomes inefficient and unworkable. Also, information is projected onto the section from varying distances. Information from further away can distort interpretation, create inaccuracies, and increase risk of misinterpreting subsurface conditions, which can lead to additional costs associated with over or under design, construction delays, and/or overall cost. The geoprofessional who embraces 3D will not only save time and effort, but can also gain a greatly enhanced insight into the project. 3D visualization of information at early stages of a site investigation allows geoprofessionals to target additional locations within the subsurface to investigate, especially for complex stratigraphy or where more information is needed for either problematic or desirable soil types and conditions. The Testing Grounds is an arts center in the Melbourne Arts Precinct that was looking to expand and develop a new wing which involved a geotechnical investigation. This is the same site as the previous slide. The geology at the site involves the Coode Island silt and a Holocene alluvium. The Coode Island silt is compressible and would settle substantially with dewatering and/or loading. Ideally, the building would be built on the stiff basalt flows, but the highly variable ground conditions across the site meant it was important to have a comprehensive boring data to better characterize the subsurface conditions. Implications to the project of building on less than ideal conditions meant that engineers needed to consider site complexity in recommending the appropriate analyses for the building addition related to total and differential settlement and different foundation options to manage financial risk to the construction and long-term performance of the building. On this slide, you can see the 3D ground model visualizing a high level of detail of the complex subsurface sediment stratigraphy. Each layer of complex geology was printed in a different color to match the digital 3D interpreted model so it could be easily seen, handled, manipulated, and explored. It allowed visitors to hold the world in their hands. There are several applications of 3D visualization, but common ones are for subsurface soil and groundwater investigations. Integrating geotechnical boring data, such as whole base or GINT logs, with 2D and 3D physical records will establish spatial representation of soil layering and bedrock depth and demonstrate the spatial representation of problem fills or soils, for example, peat, liquefiable soils, and identify voids or discontinuities, things such as sinkholes, caves, mines, or underground tanks. Hydraulic surfaces, such as water tables, can be spatially represented to visualize a change over time, whether seasonally, through drawdown, or flooding induced. These detailed views into a site, along with soil boring tests, can help identify the location of groundwater or soil contamination. This information helps with planning for supplemental soil and investigations into areas of interest identified by the data I mentioned. The geoprofessional who embraces 3D will not only save time and effort, but can also gain a greatly enhanced insight into the project. Insights such as missing soil or water information that can lead to the need to redesign before or during construction, the need to change construction methods during construction, both of which could lead to project delays and cost overruns. 3D modeling can help demonstrate missing soil information that is not identified during design or construction and could ultimately lead to long-term performance issues. A 3D view increases the chance of exposing inconsistencies or contradictions, inaccurate interpretations, and missed opportunities, while reducing risk from professional, construction, or operational perspectives. It can reveal far more effectively than in 2D methods, where data may not yet be adequately robust, detailed, or comprehensive, and where more fieldwork and testing may be needed. Many other hazards can be identified with 3D data. LiDAR, INSAR, or other methods of surfaces can be used to identify historical landslides or rockfalls in the landscape adjacent to linear infrastructure, for example, railroad tracks, pipelines, or roadways, or that have damaged linear infrastructure. Leveraging these types of 3D surfaces can provide long-term understanding, such as change detection to determine over-time movements. This will aid in identifying areas of interest for further investigation, or areas that are likely to experience catastrophic failures imminently. Other hazards can be areas of flooding that impact linear infrastructure or developed areas, and the potential impact to geotechnical structures such as culverts, levees, dams, bridges, and their abutments or wing walls. 3D modeling and scenario development assist in answering questions like, have these infrastructure components been affected? Are there water levels that have breached dams or levees, or water levels that are putting them at risk? Are there water levels that are putting culverts and bridges at risk of overtopping? Are flow velocities that incorporate stage and velocity such that bank erosion and scour will impact infrastructure? Actively analyzing risk is done using real-time or near real-time data. Visualization with program limits, for example, points on a map that will light up when an algorithm limits for alerts are triggered, is great to assist in managing assets. Contaminant modeling and contaminant remediation progress are managed through data collection and sampling methods, such as these, and provide a more rapid response to potential risk. 3D modeling can be applied by offering support and engaging client relations. It can reduce project risk, and that with more comprehensive design and construction estimates, you can yield more complete cost estimates and a more complete understanding of what equipment and methods need to be employed before site operations are initiated. This allows for better planning ahead and mitigates the risk to additional costs or delays. Increased testing of the surrounding site over long term gives better site characterization. With real-time testing, this means you have real-time data to support construction that provides a level of assurance that the site risk is being mitigated, and if any issues arise, they can be managed early on in the project lifecycle. Applications to engineering and construction support are for things such as cut and fill volume estimation at borough sites and construction sites, excavation to bedrock planning, contaminant and spoil soil volume estimation, bedrock drilling and blasting quantities, mine tailings ponds placement and removal quantities, tunneling design and excavation design, which I'll provide more examples of later on in this presentation. Building a geological model takes a lot of data, which needs to be digitized and incorporated into the 3D space. This data may include geological information, borehole sampling results, cone penetration tests, analytical results, field observations, geophysical data, construction records, survey information, and LiDAR and aerial imagery. The next step is construction of a series of geological surfaces in 3D space to define the different geological units in the model. Any additional data gathered from the site exploration can be mapped quickly on-site or in the office and can be incorporated into the dynamic model. When infrastructure is incorporated into the 3D model, the position and relationship of these features to the ground can be studied, which leads to safer and more efficient design. Sometimes infrastructure maps are localized and may not provide the correct location or the full extent of water mains, sewer lines, or gas lines, and so on. Incorporating these types of data into the model helps to point out high-risk areas so that designs can be modified to avoid conflicts in locations with abundant or complex infrastructure. Data are incorporated into a model using a complex QA/QC process, and importantly involve data that are vetted by an expert or qualified geoprofessional. While the technology and practice of 3D modeling is becoming easier to build and generate, one key part of this that remains integral to success involves the iterative process and geoprofessional input at various stages of modeling. While an initial model may be generated from more raw or initial results, this is often only a starting point to better identify where there may be data gaps and where more testing or drilling should be performed. This reduces cost on the overall project by allowing for targeted investigation, and the ease of bringing this data into a 3D environment allows for updates of new data quickly and affordably. Evaluating the overall resolution and quality of input data with continued communication between clients, contractors, and the wider project team results in thoughtful and informed drilling programs and testing plans. The image shown here is a site with a focus on the composition and relative density of the alluvial unit. There is reasonably strong clay throughout the area, but the concern for this site was low-density sand and weak clay. The ground model developed involved using a high density of cone penetration test data and a 3D interpolation of the relative stiffness of the material. The orange in this image shows the dense to very dense sand across the site. The focus wasn't on the overall geology, which wasn't modeled to a high degree, but rather on these individual sand lenses and units. The profiled ground and box cut out of the left area is an area that was backfilled. The model incorporated historic cut and fill plans and found that in the areas of historic cut, which was not modeled as natural geology, that most of the weak geology was in this historic cut area. Subsurface views of information provide insight into relationships between data and allowed for integrated views of high and low risk areas. In this case, the data speaks volumes. An area of significant risk is how 3D models are managed, which includes how data are vetted, stored, processed, and collected. The general rule is garbage in, garbage out. One way to reduce risk for this is integrated and centralized data. Providing live links to data sources are of great benefit to a project, both large and small. An example of this would be adding borehole locations that are provided as a CSV file at the start of a project. If the borings were proposed coordinates and have been surveyed since initial input, this may not be communicated to the modeler. There can be wasted effort developing the model and interpolating results only to discover the disconnect between the planned versus actual boring locations. While 3D modeling advancements give a qualified modeler the tools to rapidly generate ground models, there is still time and effort that a project budget may not be able to afford, especially if remodeling identifies knowledge gaps, soil risks, and the need for additional testing. Having an information specialist manage the data is invaluable and can greatly reduce risk. Most of our big projects involve live links to databases that are tied into integrated software to improve communication and enable efficient QA/QC, not only between the software, but between engineers, geologists, and our clients. Some of the tools that we've used are Leapfrog, Equus, ArcGIS InfraWorks, and Civil 3D. In the next few slides, I'll discuss a few case studies and examples where additional testing, drilling, and 3D subsurface investigation mitigated risk and provided overall cost saving. The Melbourne Metro Tunnel is an approximately 5.5-mile long, dual 36-foot rail tunnel under downtown Melbourne and is currently under construction. Golder has been involved since project conception in 2008. Throughout the duration of this project, 3D models were built to aid in the design of tunnels and stations, visualize groundwater, and incorporate a complex river crossing. The majority of this infrastructure is to be built underground, and the important focus has been on developing a detailed understanding of the ground conditions beneath the city, including the potential for ground movement and contamination. Geological formations along the Metro Tunnel alignment include formations ranging from the Melbourne Formation, which includes siltstone and sandstone, to Coot Island silt. Different geological conditions along the alignment contribute to groundwater quality and levels, the possible presence of heavy metals and gases, and the potential for acid sulfate soil and acid sulfate rock. Hundreds of site investigations and studies have been performed to understand the ground conditions along the proposed Metro Tunnel alignment to mitigate encountering contaminated industrial fill and the acid sulfate risk. Acid sulfate rock is when sulfuric acid is produced from soil or rock containing these naturally occurring materials after exposure to oxygen. The objective of this tunnel design is to avoid these areas, avoid hydrating these areas during construction and subsequent operation, and augment the design and choose materials to mitigate the corrosive effects of the acid should it form during construction or during its operational life. Due to this risk, the project included a substantial program of geotechnical drilling. From this information, a geological model of the ground conditions has been developed, and the 3D model has been used to determine appropriate construction techniques and options for alignment. The cost savings in this case are a result of 3D model iterations which identified optimal design alignments while avoiding acid rock sulfate and industrial waste. The Victorian government and Transurban partnered to build a $5.5 billion tunnel to improve commuting by providing a new option to cross the river and ease congestion while widening the Westgate Freeway. On this project, there were two main issues. One, the lower part of the newer volcanics was brecciated due to flowing into water and led to much different geomechanical properties. Two, the area around the backfilled section of Stony Creek was also an issue because the creek had been backfilled and the realigned freeway was built on top of the backfilled section. Upon further drilling and testing, it became clearer that the rock below the old creek channel was also found to be more fractured. The model and cross sections help demonstrate infrastructure risks, things such as water mains and sewers, the geological risks of the mixed ground conditions, stratigraphic interpretation of geology based on additional drilling and testing, hidden risks such as previously diverted creeks and industrial fill, contamination from heavy industry. All of these were used in order to provide input on tunnel options. The project was able to quickly incorporate the information from drilling programs that were ongoing at the time into the 3D model, which resulted in adjusting the final alignment to avoid the higher risk subsurface conditions. The 3D model was able to help the project team identify these hidden risks more efficiently, which assisted in a better design and an overall cost savings. This is another tunneling example for Sydney Metro Central Station. Golder was a part of a tender team and worked to develop a 3D model to support bid design. The model involved integration of Golder data, historic cross-sections from the early 1900s, as well as BIM data. The risk for this project was the presence of less stable geologic dikes versus the more stable intact sandstone unit where the tunnel was being built. The geology of the area has dikes that shoot across some of the units. However, the issue is that these geologic dikes are not common in Sydney, and while tunnels are a common infrastructure, there was a risk of complacency by assuming that the proposed location wouldn't be affected. The approach taken was to incorporate historical information along with current drilling and testing to reduce risk of encountering these dikes. While reviewing this data in 3D, they realized the dikes were in fact crossing the proposed tunnel alignment and decided on an approach to reduce risk by incorporating the dikes into the design and expanding the cut and cover section by approximately 160 feet on either side. 3D modeling was instrumental to saving on cost because the 3D modeling team was able to deliver fast cross-sections to the design team while working in conjunction with the CAD team to incorporate the dike into the main cut, as well as the BIM model and station design into the overall ground model. This approach resulted in faster construction with reduced project risk. Another case study type are landfills. Common challenges in landfill projects include protecting groundwater through proper drainage, restricting uncontrolled runoff, and most importantly, ensuring that significant groundwater resources are not jeopardized by the landfill. Understanding subsurface conditions through 3D modeling can help identify groundwater risk pathways if a release from a landfill were to occur. On the landfill expansion project, 3D modeling provided preliminary insights into the subsurface conditions of areas with low permeability through drilling, core logging, sampling, groundwater monitoring, and field observations. Additional drilling and monitoring systems were designed to allow for a more rapid response to potential groundwater risk from contaminants, and the model iterations enabled the project manager and team to see another side of their data while helping to reinforce their geologic and hydrogeologic understanding of the project site and surrounding area. Cross-sections were generated, providing a static and dynamic view of interpolated surfaces in geology. Sometimes these models remained behind the scenes, but their input was invaluable in providing a fresh perspective on existing and newer data. This example is for one of our mining clients that wanted to build evaporation ponds for a tailing facility, and in order to do that, they needed to win clay liner material. A big grid of investigation was prepared of the area to identify the best potential locations. The way this was done was by incorporating the pond design options into the 3D model and digitally excavating them out of the models for volume estimates. We were able to calculate the clay liner material to win, not only overall, but from the excavation of clay material to compacted clay material. From this exercise, we were able to choose 3 ponds that were both larger and deeper than the other 2 proposed locations because we were able to determine there would be a greater gain of clay despite the larger area and depth. The model and this information was given to the tendering parties, and they came back asking for more. We provided the 3D surfaces and an interactive model to help them evaluate the information themselves. We were then asked to provide them a 3D top of clay surface across all of the ponds, and provided another version that was lifted up by 1.5 feet. The benefit of this was they were able to feed that information into their bulldozers. The bulldozers with their GPS excavated down to the surface and didn't over-excavate. They then started excavation for clay and reduced risk by integrated 3D geology with their 3D design, which provided a more efficient excavation with 3 larger and deeper ponds than the original designs. Ultimately, the purpose of a model is to enable clients and project teams to make more informed decisions to manage risk, and this is increasingly important as infrastructure projects become bigger and more complex. The flexibility and responsiveness of 3D models allow alternative scenarios to be tested. It's possible to quickly see how the model responds to different inputs and parameters, not only in terms of the immediate location or time frame, but also from the broader perspective of flow-on effects and consequences. Multiple iterations with different inputs will offer further insights, assisting the specialist decision-making process and helping to reduce risk. The 3D model can also help reinforce or verify a specialist's interpretation, much like getting a second or third opinion. By providing this reinforcement, the model helps reduce risk and increases confidence in the specialist's interpretation and solution. As with any technology or technique, getting good results from 3D depends on using it well and wisely. This requires specialized skill sets and software, as well as good data and a clear shared understanding of the level of confidence or ambiguity in the model. The inputs need to be accurate for the model to be reliable and robust, and as more data becomes available or as conditions change, the model will need to be updated to reduce risk of an inaccurate or outdated model. An inaccurate or outdated model could cause far more problems than it solves. That said, under the right conditions, 3D modeling offers an unprecedented level of processing power translated into a form that human minds can easily interpret. With the increased perspective and clarity gained through 3D, project teams are likely to communicate key information more effectively and make better decisions, such as targeted and focused testing. These decisions influence risk, revenue, cost, efficiency, and productivity, and they determine the success of projects and businesses. Ultimately, for geologists, engineers, and related professions, 3D modeling offers an opportunity to get better results across infrastructure and geotechnical projects, particularly if project teams can see beyond the most obvious value of 3D modeling as a presentation tool, and look to embrace its power and scope for design, decision-making, and risk reduction. There is much to be gained by becoming more digitally enabled to see the biggest and clearest picture in this complex and rapidly transforming world. Thank you for your time, and please reach out to any of us for more information and to find out more about how we can support you on your projects. Have a nice day.